Hello and welcome to a video for Calculus 1. In this video, we will be talking about optimization. And for anybody following along that has a Larson Calculus textbook, this is section 3.7. So in this lesson, we will talk about the process on how to optimize and examples of optimization, but I want to make this point. This is one of the most applied things that you can do with calculus. So this actually works with real world scenarios and it helps find minimum or maximum values. So I like to think that this would be real world helpful at some point. Let's take a look at how optimization works. Here on this slide we have the process of optimizing. So the first thing you want to do is identify all given and unknown quantities. We need to know what we have available to us, what we're working with, and then we can move forward. Second, I want to draw a picture if possible. Usually drawing a picture helps with the understanding of what it is you are trying to accomplish. Third, we will need two equations. So for optimization, we will have two equations, the first being the primary equation. And this is the equation we need for the quantity to be optimized. Another way of thinking about this is that the primary equation is what we will end up taking the derivative of. The secondary equation will be used to reduce the number of variables of the primary equation. So we will have an equation that we're trying to optimize, aka find the minimum of this or the maximum of that. And we will have a secondary equation that we will generally solve for a variable and use that unknown expression to substitute into the primary equation. Then, once we have made that substitution, we will find the domain for the primary equation. And of course, we want to make sure the domain makes sense, make sure that it is reasonable. And so a lot of the times we end up ignoring negative numbers, but I will make sure to note that when I go through some examples here in a moment. The last step here is to determine the max or min, or the optimized value, usually by the first derivative test. So we will take the derivative of the primary function, we will find the critical values, and then we will check to see where the critical values have a maximum or a minimum depending upon what we're looking for. For our first example, we have this following scenario. The sum of a first number and twice a second number is 108. Find the maximum product for these two numbers. Both numbers must be positive. So what we know for sure is that x and y are going to be our numbers. So let's call x the first number, and let's call y the second number. What else do we know? We know that the sum of the first number plus twice the second number is 108. All right. The second thing we want to do here is draw a picture. And I'm going to go ahead and say that that doesn't apply here. Not applicable. The third thing we want to do is write down the two equations. The first equation that we are going to write is going to be the equation that we will be maximizing or minimizing. And since we're trying to maximize the product for these two numbers, we want to know, let's just call it big P for product, x times y. So we're trying to maximize the product of these two numbers. X times y, again, I'm calling P for product. One thing I should mention before I go any further is that one other thing we know is that x and y have to be bigger than 0. They have to be positive numbers. So the other equation here, our secondary equation, will be this one that we found right here. X plus 2y equals 108. Okay, so what we can do from here, in order to rewrite our primary equation with one variable on this side, is either solve this equation for x or for y. It doesn't matter. And since solving for x is a lot easier here, all we have to do is subtract 2y. That is what I will do. So this is part of step 3. So here we have x equals 108 minus 2y. And why we do this is that you notice that we would have some sort of product rule happening here in our equation because we have this variable and this variable, x and y. But if I substitute this value or this expression in for x, then we will have that the product, we can find the product between 108 minus 2y and y. We have reduced the number of variables in this equation down to one variable. And when I say the number of variables, I mean on the right side of this equation. So we had two different ones, x and y. Now we have one variable, it is y. All right, from here, we can do a little bit of simplification and distribute this y to the 108 minus 2y to get 108y minus 2y squared. Step 4, it was to find the domain of this new function. I'm just going to write it over here again. So we can find the domain of this function right here. What possible y values are we allowed to have? Well, since this is a polynomial, in fact a quadratic polynomial, the domain of a quadratic polynomial is all real numbers. However, way back here from part 1, we know that y has to be bigger than 0. So our domain for this particular equation is 0 to infinity. Now the last step, this is where all of the calculus happens. We have this function p equals 108y minus 2y squared. We want to find the derivative. We want to find all critical values of this derivative. There are no values where this derivative is undefined. So instead, we will set it equal to 0 and solve for y. We can add 4y to both sides and divide both sides by 4. So y equals 27. This is a critical value. When you have a critical value, we have to see if it is a maximum or a minimum using the first derivative test. So I'm going to pick 1 and I will pick 28. And we have to find f prime of 1. I'm sorry, I guess we could call it p prime of 1. P prime of 1, there we go. And p prime of 28. So when I come back and substitute 1 into this function here, I am definitely going to get something positive. Yep. So we know that it will be increasing to the left of 27. And when I substitute 28 into this function here, 4 times 28 is 112. 108 minus 112 is something that is negative. So it is decreasing here. So we are using the first derivative test again to make sure that there is a maximum at the critical value 27. The original function goes from increasing to decreasing, which means there's a relative maximum, which is what we're looking for. So we know the relative maximum will happen when the y value is 27. So what would the x value have to be? So from the previous slide, we confirmed that a relative max exists at y equals 27. We know that this equation is true, but it would make more sense for us to view this equation in the form where we solved for x, because that allows us to just substitute 27 in for y and solve for x. So with that being said, we know x equals 108 minus 2 times 27, which is equal to 54. So we know now that x equals 54 and y equals 27. The question was asking, what is the maximum product? So the last step that we have to do here is multiply these two values together. When you multiply them, you get 1,458, thereby answering the question, what is the maximum product you can get? Lastly, I want to state something about this particular example. When we found our primary equation and decreased the number of variables, we found that p equals negative 2y squared plus 108y. This is, in fact, a quadratic equation opening down. So the graph of this is a parabola. And you know that if you can find the vertex, that you can also find the solution to this equation. If you do not use calculus, chances are your calculus professor will be upset with you. While there is another way to find what the vertex of this parabola is, make sure you are using calculus. Make sure you are actually finding the derivative. Here we have our next example. This says, a Norman window is constructed by adjoining a semicircle to the top of an ordinary rectangular window. Find the dimensions of a Norman window of maximum area when the total perimeter is 16 feet. And here I've drawn a nice little picture for you. So a Norman window is exactly that, a rectangle with a semicircle at the top. So the perimeter of this window would be this. I'm going to outline in red. There we go. So if we know the perimeter is 16 feet, let's see, what do we know? We know the x is the width of the window. All right, we have to do step one here, write everything down. Width of window, we'll say in feet. Y is the height of the rectangular piece, ECE, there we go, in feet. And we know that the perimeter is 16 total feet. All right, so next we need to draw a picture if we can. A picture was provided. Very cool. Third step, we want to write down our two equations. Let me write this here. There goes 2, all right. 3, the equations. What we are trying to maximize here, let's see, maximum area. All right. So the maximum area would be the area of this rectangle plus the area of this semicircle. So let's see, I know the area would be xy plus the area of the circle. So the area of the rectangle was pretty easy to find. It's the width times the height of this rectangle. But the area of the semicircle, I misspoke. We have to figure out what that would be. We get a pretty good clue here that this length is the same as this length. Since we need pi r squared for the area of a semicircle, it looks like the radius would be half of x. So the area for the semicircle would be pi x over 2 squared, but that would all be over 2 because you want half a circle. So here's the total area for this window. And we know that the perimeter is 16 feet. That is our secondary equation. So this would be 16 equals 2y plus x. So we can get these three sides added together. Then we need to add to that the perimeter of a semicircle. And so the perimeter of a semicircle, or the circumference, is 2 pi r. In this case, r would be x over 2 still. But since we don't want the entire circumference, instead of it being 2 pi r, half of that would be pi r. And then again, we would have x over 2 as our radius. So pi times the radius, in this case, would be x over 2. So we can use this secondary equation to solve for a variable. I think it would be easiest to solve for y. So I can subtract x and pi over 2x from both sides of this equation to get this equation here. Then I can divide everything by 2 to get this equation here. Finally, what we will do is we will take this expression and substitute it in for y here. So the area equation then becomes this. And there was a small simplification here. X over 2, the quantity squared, is x over 4. We would multiply that pi by pi. So it would be pi over 4 times x squared. And we would divide all of that by 2, which would be pi over 8x squared. Now for this particular example, we know that we can find the domain for this function. It is a polynomial, so we know that the domain here would be negative infinity to infinity. But in order for this to make sense, we know that the domain should be 0 to infinity. The x value here cannot be equal to 0, and it cannot be negative, since we are talking about a distance. So let's simplify this area equation just one more time. This would be 8x minus 1/2 x squared minus pi over 4x squared plus pi over 8x squared. You could, if you wanted to, try to combine all of these x squared terms, but I think it's going to be easier just to leave them as is for right now. Alright, so we did step 4, that was find the domain. Step 5, we're going to take the derivative of this function. And there it is. And we have to set this equal to 0 and solve for x. And this time it will be necessary for us to combine these terms together. So the next step here in this particular equation, when we set the derivative equal to 0, I will subtract 8 from both sides. So I'll have negative x minus pi over 2x plus pi over 4x equals negative 8. I can common factor an x out of all of these terms here to get negative 1 minus pi over 2 plus pi over 4 times x equals negative 8. And finally, we can solve for x. Negative 8 over negative 1 minus pi over 2 plus pi over 4. And this is a really nice little expression here. I think it would be easier if we had this as an actual approximated value for it to make a little more sense. This would give you approximately 4.481 feet. So the x value here is 4.418 feet. And this, again, is our critical value. So we still have to check to see if a maximum is happening there. Let's do that on the next slide. So here on this slide, we have the derivative from the last slide, the critical value from the last slide, a number line starting at 0 and our critical value 4.481. I picked 1 to the left of 4.481, and I know it'll be something positive. So the function will be increasing between 0 and 4.481. And I picked 5 to the right of 4.481, and you'll get something that's negative, which means the original function is decreasing, which means then there is a relative max at x equals 4.481. Now, the directions asked what dimensions will give this window the maximum area. So it turns out that we know x. X will give the window maximum area. Now we have to use the perimeter equation, which we know was 16, 2y plus x plus pi times x over 2. And remember, we solved this for y, and we got y equals 8 minus x over 2 plus pi over 4x. And now all we have to do is take where we know this critical value gives us a relative maximum, substitute it in for these x's here. Whoops. There we go. And then just get back a value for y. You'll get y equals 2.240 feet out to 3 decimal places. And I did goof on the formula. I did change this to a minus. So the dimensions all in one place would be, we would want the width to be 4.481 feet and the height of the rectangular rectangular portion to be 2.240 feet. And that would guarantee that when we take half of this, or when we find the area of the rectangular piece and half of this as the radius for the semicircle, we would have the maximum area. And yet another example. A rectangle is bounded by the x-axis and the semicircle y equals square root of the quantity 9 minus x squared. Find the dimensions of the rectangle with the maximum area. So again, what we are trying to do is we are trying to write down everything we know. So at the moment, we know this equation. It's y equals square root of 9 minus x squared. We know this is a semicircle. And I think we also know that it is bounded by the x-axis. And we're looking for a rectangle area. Okay, so this one might not be as obvious to think of in pictures. So we know there has to be an x-axis, and we know that there's going to be a semicircle, and that it is a top semicircle. But what we're looking for is a rectangle that is inscribed between the x-axis and the semicircle. So there's one example. Another example of a rectangle that would fit this would be right here. We go up to the semicircle, we go over to the other half of the semicircle and go down. And what we're trying to do is we're trying to find the rectangle that has the largest area. So we can do that if we move on to step 3, which is get our equations down. So our equations, one of them was given to us. That is y equals square root of 9 minus x squared. And the other equation here is the area is going to be 2x times y. And that is because when you come back up here, you'll notice that if we only take x times y, x will only be the distance from the y-axis. That will only be the right component. So we also need to go left the same amount of x. So 1x plus another x would be 2x. Same thing with the blue rectangle I drew here. So it would be 2x times y. So then we can just simply, we can simply substitute this in for y, and we can have this new area that we are trying to maximize at 2x times 9 minus x squared to the 1/2. And what this does right here is it creates a product rule. So before we get into that, I want to discuss what the domain of this function is. And you can see here with the semicircle being drawn, remember if you have a number, a perfect square number minus x squared and a square root, that's the top half of a semicircle. But whatever number is being squared here to give you 9, that will be your radius. So I know here that the radius is 3. So our domain for this particular function, we can't go outside of -3 to 3. So there's step 4, way down there. So now we have this area function that we are trying to maximize. 2x times 9 minus x squared to the 1/2. So again, if you think of this as f of x, then we know f prime of x pretty easily is going to be 2. And if you think of this one as g of x, then g prime of x will require the chain rule, and the derivative will be 1 over 2 times 9 minus x squared to the 1/2 times the derivative of the inside, which would be negative 2x. And there is a simplification we can make here. This 2 will always reduce with this 2. So then we can simply just rewrite this would be negative x in the numerator. If I move this negative and this x into the numerator. So it would be negative x over 9 minus x squared all to the 1/2. So now that we have all of that together, we can find that the area, or the derivative of the area function, would be the first times the derivative of the second. 9 minus x squared to the 1/2 plus the second times the derivative of the first. It appears I put too much here. The derivative of the first is just 2. There we go. So now we have the task of finding the critical values for this particular function. So I know already I've got 2 critical values at x equals 3 and negative 3. The endpoints of this semicircle here are always going to give us some critical values. And that's because at those endpoints, there are vertical tangent lines. They have infinite slope, so we cannot include those. Next, what we can do is set this entire function equal to 0 and solve for x. So with a little bit of simplification, I will set it equal to 0. I'm going to combine these two here on the top. That would be negative 2x squared all over 9 minus x squared to the 1/2 plus 2 times 9 minus x squared to the 1/2 equals 0. Now in order to solve for this, I'm going to multiply both sides by 9 minus x squared to the 1/2. So when I do that, this term, it would completely cancel, but this term here, it would square it. And so these two exponents would combine to be 1. So what that means is then we have a derivative, or we have a simplified function that would be negative 2x squared plus 2 times 9 minus x squared equals 0. Yeah, it ends up being that simple. So next, I can distribute this 2, get negative 2x squared plus 18 minus 2 more x squared equals 0. I can subtract 18 from both sides and combine the negative 2x squareds to get negative 4x squared equals negative 18. I can do a little bit of dividing here. I get x squared equal to 9 over 2, which tells me that x would equal plus or minus 3 over square root of 2. All right, On this slide, we are continuing the previous example. Here was the derivative. Here are the critical values, which are approximately not 1.65. They are approximately 2.12. So then what we can do is we can set up our number line between -3 and +3. We have -3 square root of 2 as our critical value and +3 over square root of 2 as another critical value. And the reason we like the approximation is it tells me what values I can pick between 2.12 and 3, or -3 and -2.12. So it gives me these values here. And then 0, if you can pick 0, you want to pick 0. So as far as this is concerned, the derivative when x equals -2.5 was negative. So it is decreasing on this interval. The derivative when x equals 0 is positive. So it'll be increasing on this interval. And then it will be negative when when x equals 2.5. And since we are looking for a maximum, we will be picking 3 over square root of 2, because that's where the graph, the original function, stops increasing and starts decreasing. This would be a relative max. Whereas this would give you a relative minimum. So this is the value we want, and so x totally will equal 3 over square root of 2. So then to figure out what y equals, we bring back the equation for y, which was the square root of 9 minus x squared. We can substitute this value in for x, and it'll end up being 9 over 4 after you square it. And when you subtract 9 over 4 from 9, you will get that y value will also be 3 over square root of 2. But remember, the dimensions are the height of the rectangle, which is in fact the y value. But the width of the rectangle would be 2 times this amount. So for this, we would need 2x, and that would just be 6 over square root of 2. Now, if you like rationalizing, this is equivalent to saying 3 square root of 2 over 2, and this is equivalent to saying 3 square root of 2. But just for simplification purposes, these are good answers for me. And these are more traditional answers you would find, say, in the back of the book or something like that. One more example. Hang in there, everybody. Last example. A farmer wants to find the largest pen he can build with 440 feet of fencing. Using the template below, what are the dimensions that maximize the pen's area? Okay, so we have a picture already. That is step 2. There we go. Step 1 is to write down what you know. We have 440 feet of fencing. That's good to know. It looks like we will have 3 equal pens for whatever type of animals this farmer is trying to make. And let's jump right into step 3. We know the area of this given rectangle, our primary equation would be x times y. And the farmer has 440 total feet of fencing, which means we need basically a fence wall here and here. So that would be 2 x's. And then 1, 2, 3, 4 walls going this way. So that would be 4 Ys. So the total number of fencing, or the total number of feet of fencing, would have to equate 2 X's plus 4 Ys. So we can solve this. I'm going to solve this for X, because if you solve this for Y, eventually you'll have to divide by 4. And that means you'd end up with a fraction. And I want to avoid fractions as much as you want to avoid fractions. So if we solve this for X, we can divide everything by 2. And we can see that X would equal 220 minus 2Y. Then I can substitute that right back in for X. And then we can start talking about the domain and finding the derivative. So step 4, we have this function, 220 minus 2y times y. All right, in fact, we can do better. Let's simplify that. 220 y minus 2y squared. There it is. The domain for this function, again, would be all real numbers normally, but since we are dealing with distances, we're going to say 0 to infinity. So then we can jump right over into the derivative. A prime equals 220 minus 4y. And we can set that equal to 0 and solve for y, and y will end up being 55. All right, really quick check here. Here's 55. We can't be less than 0. So why don't we pick 1, and we can pick 56. So if you pick 1, a prime of 1 would be a positive value, which means it would be increasing here. A prime of 56 would be a negative value, which means it would be decreasing here, which means we have a relative maximum at y equals 55. That's exactly what we were looking for. So y equaling 55, we can use this value over here in our equation that's already solved for x, and we can get an x value of being 110. All right, I hope this lesson helps with your understanding of optimization. Good luck.